Hi viewers, welcome to LMS Solution. Today we are going to see about hybrid AC-DC microgrid and its coordination control. So first we are going to see about the block diagram of hybrid AC-DC microgrid. This system going to be implemented in MATLAB simulation. First we have to discuss about this basic block diagram. This is a basic block diagram of hybrid AC-DC microgrid. It consists of solar PV panel and then boost converter and then DC load, and then it have battery storage system. It have bidirectional converter. This section is solar PV with the boost converter, DC load, and bidirectional converter battery is going to be considered as DC microgrid. And then the DC bus going to be connected to the AC system. So via this main converter, this is the voltage source converter. This AC voltage source converter, that means it's going to act as a bidirectional DC-DC inverter or converter. It also act as a bidirectional converter. Can take power from that means it can allow the power flow between DC microgrid to AC microgrid, and then AC microgrid to DC microgrid. This converter going to be connected with the AC microgrid system. AC microgrid. So this is AC microgrid system. It consists of utility grid, and then wind energy system consists of DFIG, double field induction generator. This whole setup going to be act as a AC grid. Here we have AC load. Here we are going to implement the same concept, same block diagram in MATLAB. That means this is known as hybrid AC DC microgrid. That means we are going to use both DC grid and the AC grid to supply the power to the DC load as well as AC load. The power going to be exchanged in between AC grid to DC grid and DC grid to AC grid. Next we go to see about that MATLAB implementation of this same system. Whatever we saw that in the block diagram to implement the MATLAB. This is the implemented diagram for that hybrid AC DC microgrid system. This system consists of the battery, and then this is known as DC load, and then this is known as bidirectional converter, and this is known as solar PV power the grid connected system. So it consists of two-stage conversion, double stage conversion. Then main consists of boost converter and inverter, and then it consists of DFIG wind turbine, and then main grid, and then two AC load. Whatever we saw in that block diagram, the same thing will be implemented in the MATLAB. So we will see the detail of the power rating in the each system. So first we consider battery. Battery nominal voltage here consider as 300, and the rated capacity of the battery is 400 Ah, and then state of charge of my battery is 71%. And then and that means here you can see the DC load. DC load power is 15 kilowatts. Only we consider a resistive load. Just we consider active power. Active power is 15 kilowatt. And then go inside that a double stage connected solar PV system. It consists of solar PV panel. Here we are using 15 parallel panel and then 10 series panel. Each panel single panel rating is 228 watts, and then voltage rating is 29.9 volt, and then current is 7.65 amps. This is 37.1 is open circuit voltage and 8.18 is the short circuit current. This is the PV and IV characteristics of that consider solar PV array or different irradiation condition. For 1000 watts per meter square, maximum that means maximum power is around 34 kilowatts, and then maximum voltage is around 290. For 500 watts per meter square, the maximum power is 17 kilowatts, and then voltage would be 300.5 volt. For 100 watts per meter square, the power is around 3.3 kilowatts. Voltage is around 288 to 286.7 volt. This is a PV and IV characteristics of the consider solar PV array. Maximum rating is around 34 kilowatt, and then is going to be connected with the boost converter. After boost converter, we are going to use a grid inverter. 3-level grid inverter, and then connected to the DC grid via harmonic filter and a transformer. And here we are having inverter as well as boost converter control. Here we are using for controlling the boost converter, we are using P&O MPPT algorithm. For controlling the inverter, we are using a DQ control method. P&O MPPT received PV voltage and PV current, and it generates some reference voltage. So this reference voltage can be converted with that output of the boost converter voltage is processed via PA controller, and then when we process via generator, it when we generate the pulse for vector boost converter. So next you have to measure that the inverter output voltage and current that going to be converted into a DQ frame, ABC to DQ, and then you have to provide a reference current. This reference current will be generated based upon SoC of the battery. Here, so we have created two logic. This is less than 30%. We are taking power from the grid. When SoC is greater than 70, we are going to provide power to the grid. This is two logic we are created. Based upon this logic, the reference current will be fixed here. And then when we process via the current regulator, and then we have to generate the controlled signal based upon that DQ, that means after current controller. The output of current controller going to be used to for getting that modulating signals to generate the pulse for that inverter, and then going to be connected to the grid system. Next, you have to see the power rating of DFIG. The power rating of a turbine is 45 kilowatts, and then power rating of that generator is 45 kilowatt divided by 0.9, and then it's going to be connected with this system. And then here the wind speed is changed from 12.9 meter per second after 10 seconds, and here you can see that irradiation keep on changing. That means every 2 seconds you have to change the irradiation. That means here we are changing irradiation from 1000 to 800, 600, 400, 200 and 0, and then 200, 400, 600, 800, 1000. So we are changing the irradiation for every 2 seconds, and then you have to check the result. And also here you can see that the AC load is around 17.5 kilowatt, and then another load around 12.5 kilowatt. So here we are measuring the power of the grid. This is used for measuring the power of the grid in kilowatt. This is used for measuring the power of the PV array. These two are used for measuring the power of the AC load, and this is used for measuring the power of the battery, and then this is used for measuring the power of the wind turbine. And here we are using voltage control DC bus, that means DC grid voltage control. Here we are going to measure the DC link voltage and compare with the 470. Here DC bus voltage maintained at 470 volt, and going to be processed via PA controller and processed via Bidirectional generator. It going to be generate the pulse for this bidirectional converter not to maintain the voltage around 470 volt in the DC bus. Here we are going to measure the DC bus details, that means DC bus voltage, DC load, power, current. And here we are measuring the battery SoC and battery current, and then here also you are measuring the battery voltage, current and power. Already the model is simulated. Let me discuss about the results. Here the detail. Here you can see that initially from 0 to 10 second, the power of the grid is negative. That's mean the grid receiving power from the DC grid as well as wind generator. After 10 second, what happened that grid power is set nearest to 0, because initially wind power is around 10 kilowatt. After that, from 0 to 10 second, the speed is maintained at 12 meter per second. After 10 second, that the speed is changed from 12 meter per second to 9 meter per second. Because of that, power is reducing here. Because of that, what happened? Power given to that grid going to be reduced. That's why the power is decreased. That means, and power in the negative region goes to near up to 0 because of reduction in the wind power, because of reduction in the winds. And here you can see that the variation of this one is solar PV power and battery power. Based upon the solar PV power, you can see the battery charging and discharging condition. Initially, the solar PV power is around 33 kilowatt. During that time, the battery goes to charging mode. After every 2 seconds, the radiation change from 1000 to 800, and then 600 and 400 and then 200 and then 0. Announcing goes to 200, 400, 600, 800. Because of this reduction in the radiation, what happened in the battery power? Battery moved from charging stage to discharging stage because of power reduction in the PV panel. Because of radiation change, there will be a coordinate control between the solar PV and the battery system. And then here you can see that the load is continuously getting power from the AC and DC microgrid. Next you have to see about DC load. Here you can see that this is a duty cycle for the bidirectional DC converter, and then this is a DC link voltage maintained at around 470 volt, and then this is DC load current and then DC load power. So DC load power maintained at 15 kilowatt. All operating condition of being solar PV system. Next you have to see about the source. Here you can see that initially the battery goes to some charging mode initially, but after 2 seconds the radiation change to 1800 watts. Because of that, so battery try to manage the power supply. It try to supply the DC load as well as AC load. That's why SOCs keep on decreasing here. This variation of current initially in charging mode, and then after 2 seconds goes to discharging mode, and then come back to the charging mode according with the solar PV irradiation. It's a detail of battery current and SOC. Here you can see that this is a battery voltage, battery current, and then battery power and SOC of the battery. Same thing. It will be changed according with the change in irradiation PV power. This is a total operation of hybrid AC and DC microgrid system. Thank you for watching our videos. Kindly subscribe our channel and also click bell icon for notification about upcoming videos. Thank you. Thank you so much. Bye bye.